Hi everyone, this is the intermediate section of the lecture on probabilistic decision making. The subject is special chapters of higher mathematics. In previous video we stopped at this formal procedure for probabilistic decision making where we try to maximize the expected monetary value. Now let's get to this example. We've considered some advantages. Now let's get to this example. We formally represent the problem at hand by setting up a payoff matrix. So the columns of the matrix will be representing the different states of nature. Formally, we denote them as S sub 1 state of nature, first state of nature, S sub 2 and S sub 3. As shown here, states of nature. Every state of nature is assigned a probability or odds with which every particular state of nature will turn up. So the columns represent payoff depending on different states of nature. Now the rows of this matrix represent the payoffs depending on the strategy. We have 4 different strategies available for a decision maker. We denote them formally as A sub 1, A sub 2, A sub 3, and A sub 4. Different strategies as shown here. Now, at the cross points between rows and columns, we get individual payoffs. Which show us or show a decision maker a possible benefit from adopting a particular strategy, but we've got additional information about different states of nature. We've got some odds. So we can judge by these odds which of the possible states of nature is more probable. So let's consider formally this example. Now we need to calculate the expected monetary value for every strategy. This expected monetary value will account for individual payoffs represented in a particular strategy depending on different states of nature and the odds. So we multiply the corresponding payoff, for example 20, the payoff representing the outcome of strategy A1 if the nature will turn up to its state S sub 1. So we multiply this payoff by the odds, by the probability of this particular state of nature, which is 0.2. And we multiply the second payoff of 30, which will be obtained if the nature will turn up to be in its state number 2, and multiply this particular payoff by this probability of this particular state of nature. And we multiply the third payoff of 15 for the state of nature S sub 3. We multiply this payoff by the probability of this particular state of nature, and we add everything up. So 20 times 0.2 plus 30 times 0.5 plus 15 times 0.3, we get, for this particular strategy A1, we get the expected monetary value of 23.5. Now we repeat the same procedure for the second option, for the second decision making option. We multiply the payoffs in this particular row by the probabilities corresponding to individual states of nature, and sum things up, add things up. So 75 times 0.2 plus 20 times 0.5 plus 35 times 0.3. We get 35.5. we repeat the same procedure for these two rows, for the rest two rows. So we get 52.5 and we get 33 as expected monetary value for the third and fourth decision-making options. Now we need to maximize this expected monetary value. We just do this by picking the decision-making option which maximizes this expected monetary value. In this particular case, the decision option A sub 3 seems to be optimal. It has the maximum expected monetary value of 52.5. So this is the most common criterion in probabilistic decision making. Maximum of expected monetary value. So you can consider different payoff matrices, but the procedure will be the same. The matrix may contain more states of nature or less states of nature. It may contain more decision-making options or less decision-making options. But the basic idea is the same. You just multiply the payoffs corresponding for a decision, the payoffs of individual decision-making option times the probabilities of different states of nature and sum things up. And then pick up the maximum. Now this matrix, this payoff matrix, can be turned into a tree of decisions. Sometimes it's more convenient to have this matrix in form of a tree, especially in the next stages. At the next stages, when we'll deal with the games, actual games against the counterpart. Now we're playing against nature, so there's only one person making decisions. Nature doesn't play against you. Nature just turns up in one of its states. So, but sometimes it's convenient to turn this payoff matrix into a tree. It can be easily done. We just add additional node and put some branches. So this additional node serves us as a branching point where we have in this case we have 4 decision-making options. This means that we start 4 different branches from this particular starting point. So we have the first branch leading us to the decision option A sub 1, second branch leading us to the decision point A sub 2, the third and the fourth accordingly. Now at every decision point, for example A sub 1, we have 3 different outcomes, or we may have 3 different outcomes which depend on different states of nature. Now as we made our decision, now it's nature's turn to make the move. So the outcomes will be expressed in forms of different payoffs obtained by the decision maker. For example, if the decision maker picks the option A sub 1 as his decision, then depending on the different states of nature, he may obtain the payoff of 20 if the nature plays the state S sub 1, or the decision maker can obtain the payoff of 30 if the nature plays S sub 2 or turns up to be in its state S sub 2, or the payoff of 15 if the nature plays S sub 3. Formally speaking, well, so the same happens with the second decision option. Like these payoffs here at the branching, at these branches, they have direct correspondence to these payoffs represented in the matrix. These odds or probabilities of different states of nature, we just put them, these probabilities here, just for our information. So now we can compute different expected monetary value by multiplying these probabilities of different states of nature times payoffs and sum things up. So this is it for this video, and in the next video we'll get to the advanced section where we consider this particular example given by MIT.